Homework 14, Rational Functions, Video 2, Vertical Asymptotes. Before we get into this discussion, I want to introduce a symbol to you. It's a very easy symbol. It's an arrow pointing to the right, and it's a symbol for the word approaches, which means gets closer to. So let's start by defining what a vertical asymptote actually is. Graphically speaking, a vertical asymptote is a vertical line. So as a consequence, its equation is x equals some number. We'll call that number c. But a vertical asymptote is a vertical line x equals c, such that as a graph approaches the vertical line, either y approaches infinity, or y approaches negative infinity. In other words, it's like an invisible boundary, vertical, that as the graph gets closer to, it's going to do one of two things. Either the y value is going to approach infinity, or the y value is going to approach at negative infinity. But you can never actually cross a vertical asymptote, and you'll see why in just a moment. Below here, I've got three functions that we're going to find the vertical asymptotes for. But since we're not having a dialogue as opposed to a monologue, I'm not going to take you through the discovery process of figuring out what constitutes a vertical asymptote. So I'll just tell you how to locate vertical asymptotes, abbreviated VAs. The first thing you do is solve the denominator equal to 0. This kind of makes sense because your vertical asymptote will occur where your function doesn't. So as you're getting closer to the graph, as you're getting closer to the vertical asymptote, the graph will get closer and closer and closer, but never actually touch it. Why? Because the function is undefined there. And where is a rational function undefined? Where its denominator is equal to 0. But there's a little bit more to it than that. You start by solving the denominator equal to 0, but then you have to check those answers with the numerator. If a value x equals c from part 1 makes the numerator not 0, in other words, you got an answer from the bottom and you plug it into the top and it doesn't give you 0, then that number is a vertical asymptote. Otherwise, it's a hole in the graph, as you'll see here in just a moment. So the process for locating vertical asymptotes is actually very straightforward. Let's take a look at this first example, f of x equals x plus 3 over x squared minus 4. We start by solving the denominator equal to 0, as if we were locating numbers to exclude from the domain. This is just a basic quadratic equation. You could factor it. You can move the 4 over in square root, but don't forget the plus minus. Well, we would get two solutions, x equals 2 and x equals negative 2. And then the second thing you have to do is to check with the numerator. Because to be a vertical asymptote, you have to make the bottom equal to 0, but not the top. In the event that there's some really sophisticated mathematician watching this, I know that there are exceptions to that rule, but for our purposes, if you make the bottom equal to 0, but not the top, you're a vertical asymptote. So let's start by checking x equal 2 in the numerator. If we put 2 in the numerator, we get 2 plus 3, which is not equal to 0. It's equal to 5. And if we put in negative 2, we get negative 2 plus 3, which is also not 0. I don't care what it equals. All I care is it's not 0. The conclusion that you would draw, therefore, and I think I've shown you the 3-dot triangle before, but in the event that I haven't, it's an abbreviation. It's a symbol for the word therefore. It usually means you're about to draw a conclusion. Therefore, x equals 2 and x equals negative 2 are VAs. So if we were sketching this graph, we would draw vertical asymptotes at both of those x values. In one of the examples, we will have a function with two vertical asymptotes. Let's take a look at the second example. F of x equals 2x minus 4 over x squared minus 4. Again, we're going to follow the same two-step process. We're going to start by solving the denominator equal to 0, and we're going to get the same two x values as before. X equals 2 and x equals negative 2. But in order to christen them vertical asymptotes, you must first check the numerator. Or rather, you must next check the numerator. we first solve the denominator equal to 0. So we'll start with x equals 2. If we put 2 into the numerator, we get 2 times 2 minus 4, and that is equal to 0. But if we put negative 2 into the numerator, we get 2 times negative 2 minus 4, which is not 0, it's negative 8. So the conclusion that we would draw is that x equals 2 is a whole, and x equals negative 2 is a vertical asymptote. Now you won't be drawing any that actually have holes in graphs, but I'll just show you really quickly what it would look like. If I have a vertical asymptote at negative 2, that means back here at negative 2 I would drop a vertical line, and the graph would either come high or come low from one side and go across. But over here at 2, we would have to put a hole in the graph. If we had unlimited time, we would talk about a lot more about asymptotes versus holes in graphs, because there's a really bad math joke about not knowing the difference between your asymptote and a hole in the graph, but all I can tell you is the punchline. Let's take a look at the last example. F of x equals x squared over x squared plus 1. If we start with the first step of solving x squared plus 1 equals 0, we can solve that easily by moving the negative 1 over and then square rooting, but we would get two answers. We would get I and negative I. But here's the problem with saying I and negative I. Asymptotes are graph things. Graphs live on an x and a y axis where only real numbers play. There are no imaginary numbers on the graph, on the coordinate plane where we sketch graphs. So, if you are locating vertical asymptotes and the answers to the first step are not real, there are no vertical asymptotes. Vertical asymptotes by default are real numbers, or their equations are x equals a real number. And so if you get x equals a complex number or an imaginary number, then it's not a vertical asymptote. So this function would actually have no vertical asymptotes, and if you think about it, it makes sense. There are no real numbers that would make the denominator equal to 0. So locating vertical asymptotes is pretty straightforward. Solve the denominator equal to 0, check it against the numerator. If it doesn't make the numerator 0, you're a vertical asymptote. But if it does, you're actually a hole in the graph.